This presentation will cover the control of a flapping plate shape with fluidic flexible matrix composites. The first part of the presentation will be done by Oscar Johansson, and the second part will be presented by Blake Armstrong. The authors would like to thank the National Science Foundation for funding this project. The main motivation behind this project is to better understand and utilize passive and active reconfiguration, both of which occur in nature. For example, there is a passive reconfiguration of seagrass in a current, as well as the active reconfiguration of manta ray fins as they glide through the water. The work in this paper is a small part of a larger project aimed at subjecting plates to an oscillatory heaving motion, where they will undergo active reconfiguration or controlled shape change in order to better understand complex fluid structure interactions. In this talk, we focus on the design of an actuated panel made of flexible fluidic matrix composites, F2MC tubes, embedded in silicone, as well as the analytical models developed to predict the shape of the actuated panels. For this project, both Euler-Bernoulli and Timoshenko beam theories were used. In developing an analytic model to predict the deformed shape of the panel, we started by applying a tip moment using Euler-Bernoulli beam theory to the end of the plate equal to the force exerted by the F2MC tube times the distance of the tube from the plate's neutral axis. However, this does not take into account the tube exerting an eccentric axial force along the entire length of the plate. So we derived a new set of governing beam equations to take into account what then becomes a distributed moment. Both Euler-Bernoulli and Timoshenko beam theories were used in this case to see whether Timoshenko beam theory can more accurately predict plate behavior at the large deflections that are seen in this study. The distributed load acting on the plate consists of the beam's self-weight and the hydrostatic pressure or buoyancy of the panel in water. To experimentally measure plate deflection, we set up the panel as shown on the right. Experiments were conducted in both air and water, with the depth of submergence in water being 16.5 centimeters. The deflection of the plate was captured using a high-speed camera recording at 2,000 frames per second. To make the panel, we first start by making F2MC tubes, which are comprised of braided PET plastic encased in silicone. Then using a mold, layers of silicone were poured with F2MC tubes in between, with one end of the tube sticking out of the plate. The final plate has two rows of tubes, one on top and one on the bottom. This creates that distributed moment that was discussed earlier. And here we see the videos of the plate deflection. On the left side is a plate in air, on the right side is a plate in water. You'll notice that the plate oscillates as the F2MC tubes are deflected. When taking data, we wait until the oscillation to stop, so until the plate reached a steady state before applying the edge detection. To measure the experimental deflection of the panel, a gradient-based edge detection technique was used to pinpoint the bottom edge of the white plate against the black background for both initial and deformed configurations. A calibration checkerboard was then used to relate the pixel locations of the detected edge to physical distances.
Looking at experimental results, we can see the plate from edge detection in the plots on the right. The top is the plate in the air experiments, while the bottom plot shows the plate in water. We can see in the air that the plate initially has a sagged shape due to its self-weight, while in water, it appears to be about neutrally buoyant due to the buoyant forces. The plates were then actuated at 10 psi, 20 psi, and 30 psi. We can see as the plates are actuated at increasing pressures, the plate deforms upwards, increasing amounts. These tip deflections can be seen in the table in the slide. It was found that in water, the plate deformed about 7.8% less as compared to the air experiments. Now comparing the experimental data to the models, we can see the models plotted with the experimental data in purple, with the air experiments on the left plot and the water on the right. In this initial position, we see the plates in the unactuated state along with their experimental predictions. In both cases, the Euler-Bernoulli models show that they predict approximately the true deflections found in the experiments, while the Timoshenko is only accurate for water while grossly over-exaggerating the deflection due to self-weight in the air. Then we actuate the model and analytical models at 10 psi, 20 psi, and 30 psi. It can be seen that the models then begin to underestimate the influence of the F2MC actuation, with the equivalent tip moment model best predicting the true deflection seen in the experimental data. Now comparing the models to each other, we can once again see the experimental data in purple with each of the models in their respective color. At 0 psi, we can see what was shown in the last plots with the Euler-Bernoulli models closely predicting the true deformation due to self-weight, with the Timoshenko model exaggerating the downward deflection. Then we actuate the models at 10 psi, 20 psi, and 30 psi, and we can see once again, as actuation pressure increases and the models deflect upward, the equivalent tip moment best predicts the deflection, while both of the distributed moments continue to underestimate the experimental data. In summary, the beam models were derived using Euler-Bernoulli and Timoshenko beam theories, with actuation of the F2MCs modeled with a tip moment or with a distributed moment. The plate was manufactured from braided PET plastic along with dragon skin silicone. It was found that the F2MC tubes were effective at controlling deformations, creating large deformations at relatively low pressures. The Euler-Bernoulli beam theory model with a tip moment was found to be most accurate at estimating the deflections, and the Timoshenko model, which relies on shear modulus in its formulation, underestimated it, although the shear modulus has yet to be confirmed experimentally. Looking to future works, we will create more panels to test with more rows to observe the effect of increasing the number of tubes. We will expand our models to look at the dynamic loading and dynamic structural responses. We will also continue our work in modeling the static tests, and more static tests will be done at water at different depths to determine the effects of the free surface. We will also test the model with controlled oscillatory heaving motions to find the behavior of the plate and F2MCs under a heaving motion. Thank you for your attention during this presentation.